we need to move to the next presenter. So thank you very much for your presentations.
Thank you.
So the next presentation is Sebastian's. And if you're ready to present, please start your presentations.
Yes, hello. Can you hear me, everybody?
Yes, we can hear you.
Good. First of all, I'm really, really sorry and a little bit sad that I can't be there in person. I'm in Kathmandu, but unfortunately became sick, so I have to do this remotely. I was very much hoping to meet you all in person and also demonstrate some of the technologies hands-on. Unfortunately, now we cannot do that. You should now be able to see my screen, I hope.
Yes, we can see.
Good. Yes. So perspective in small satellite IoT networking. This will very much connect to what Amano just talked about. Briefly, who am I? I'm a physicist by background, have done 25 years of wireless networking in various forms. Today at the IT University of Copenhagen as research lab manager, and also working with the NSRC as network trainer and developer. So what is it that's new about satellites? Satellites as communication platforms aren't really a new thing. They have been around for some decades. Iridium is probably a name that many have heard. Their commercial service has been around for, I think, about 30 plus years. But there is new and very exciting things happening that are important for IoT. Those new qualities are extreme low power, low cost, and small size of equipment. And this largely comes from two different developments in two different areas. The one is the trend towards really, really small satellites, CubeSats, and even smaller than that. We'll show you a few in a moment. And there's the progress in the LPWAN standards that Amano just talked about, most of all LoRaWAN. There is already now a number of commercial companies that offer satellite IoT services. This is my latest update of my list, but it's changing week to week. I'm highlighting two names here, Lacuna and Swarm. This is not to say that I recommend them necessarily over the others. It is just the ones that I have worked mostly with. In particular, I've been beta testing with Lacuna for quite some time because they've been very open to work with research and education, and I'm very grateful for that. But there are many, many others also offering this. Just a brief reminder, maybe this is mainly happening on two satellite orbits. One, the so-called low Earth orbits, between 200 and 1,000 kilometers. This is where the International Space Station is. This is where Starlink satellites are. The other one being geostationary, meaning remaining above one point on Earth. And that's at a very much larger height at 35,000 kilometers. These are the two classes of orbits interesting to us. Most of the new activity happens in the low Earth orbit. What do these orbits look like? This is actually taken this morning. This is a Lacuna satellite, two of its loops around the planet. It comes by sort of every 90 minutes for one trip around the planet. So as the Earth turns underneath it, you can see these passages over a certain region. And so one satellite would come by a certain location about twice a day. And twice a day, you would be able to make contact to this particular satellite. But the constellations, of course, have many more than just one satellite up in orbit. I talked about the changes here that are happening and that are really, really interesting for IoT. Let's look at a node device, a sensor device. So the power consumption of these are now in the milliwatt class rather than many, many tens of watts, like, for example, a Starlink terminal. The cost of such devices is currently in the $100 class, bit more, bit less. You can also build your own. You can actually, in the same spirit that we have in the Maker community, in the Arduino community, you can build your own end devices to communicate with such satellite networks. The cost of service, it is still developing, as many companies are sort of now beginning to approach the commercial market, but it's typically a few dollars per device and month. And device here can mean different things. We'll get back to that. The devices are rather small. The one thing that dominates the size is still the antenna, which you can see in this box here. It's the piece in the middle. It's basically a PCB printed antenna, which has a size of 6-7 centimeters. A lot of the hardware and software is open sourced and accessible to doing your own variations of it. Now, Armando talked about LoRa being extreme low power and long distance. The current absolute world record is a bounce off the moon, 700,000 kilometers. However, that was a strongly amplified LoRa signal. With normal LoRaWAN devices, much like terrestrial LoRaWAN, we can routinely talk to satellites that are 400, 500, up to 1,500 kilometers away. We're doing this with the boxes you just saw, 10 centimeter running on battery, and we're doing this every day and running on one battery for many, many, many months. The reason LoRa is so exceptionally good at long distance, again, Armando named it, the core of this is really the way it modulates its signal, the so-called chirp spread spectrum, which leads to receiver sensitivities that can go all the way down to minus 150 dBm. That, compared to Wi-Fi and cellular technologies, is about 4 or 5 orders of magnitude better. The most popular frequency bands are ISM bands, 433, then the group of 868, 902, 915 megahertz, and recently also at 2.4 gigahertz. I'll get back to that in a moment. So LoRa is already very, very strong in long distance terrestrial. I'll show a few examples. So here's the small country of Denmark, north of Germany, Copenhagen, where I live, Berlin, where I come from, and I take a bus and ferry trip from Copenhagen to Berlin, and I keep my LoRa mapping device communicating while I'm doing this. If you look at the lower part of my journey, that's the boat trip from an island of Denmark to Germany, and you see these purple connection lines. These are all measured LoRaWAN connections that we registered, and they're all about somewhere between 100 and 200 kilometers. We can even reach the boat from Copenhagen as we land in northern Germany. That's about 200 kilometers, a little bit more than 200 kilometers. And this is still terrestrial. Here's another example, the north of the UK, the north of Scotland, the islands of Orkney. And we placed one main gateway on a tower on the mainland, and it is capable of covering basically a lot of small islands. Distances here are up to 80 to 100 kilometers. So one single gateway actually is capable of reaching all of these islands. The gateway is pretty high up in this case. It's about 300 meters above sea level. Abhi said earlier that Nepal is challenging in IoT because it has a very distinct geography. However, this special topology of Nepal, the fact that we go from lowland, mid-height level to extreme high territory offers fascinating opportunities because you can actually reach a lot of the mountain region from lower parts of Nepal. What you see here is a link simulation. I just chose some pretty random places to demonstrate what I'm talking about. Simplified, you could say, whatever the eye can see on a day with clear skies, you could also make LoRa connection through. So you would probably be able to cover a lot of the mountain region from lower points of Nepal. Good, but however, when terrestrial connectivity is not an option, then you can go up to satellite. And here's the scheme of it. You can go either direct from a sensor node to the satellite, or you can go via a terrestrial gateway, which then sends up signals to the satellite. And from there on, it's over a downlink, a ground station, and from there on, conventional IoT backbone infrastructure, the network servers, the application servers, very identical to what we're normally doing when we're doing terrestrial deployments. The Lacuna satellites, for example, they are linked into the Things Network platform, and they appear as gateways just like any other gateway. They just happen to be on a satellite. So satellite LoRa can be the right choice when to send at low power. If that's not the case, don't do satellite just because you can. You might have better options. Let's look at three scenarios that we find particularly interesting. One is tracking people in the mountains. Again, Abhimanyu talked about the lives being lost in tourism every year. Carrying a small device on your backpack, which is able to communicate your location, could probably help address this problem. Number two, everything that's happening at sea. Out at sea, we typically don't have mobile coverage. We typically don't have Wi-Fi or any other network. Satellite can be an option here. We're having very fruitful dialogues at the moment with fishery management and tourism management ministries in Eastern Africa. We're talking about environmental monitoring on coral reefs off the coast. This is where satellite connectivity comes in as really well suited. Lastly, a lot of interest in wildlife tracking, be it animals or tracking the level of water in water holes or the humidity of soil in faraway places, and so forth and so forth. Here's some of our experiences with the systems as they exist today. This one is using swarm space LoRa, and we sent sailing boats from Denmark to the UK and then further on to Madeira and the Canaris Islands, and we were able to follow the boats almost uninterrupted, constantly using a solar-powered little swarm satellite device. This is what the swarm satellites look like. They are absolutely amazing. They are 1/4 of a CubeSat in size. That means 10 by 10 by 2.5 centimeters. They're basically the size of a sandwich, which also means that they can be very cheaply deployed. They're just packed up in stacks and released into space in large numbers. This indirectly makes the service come down in cost. That's why it's relevant, because launching a satellite, you pay by the size and the weight. And the smaller we get, the cheaper the service gets. This is the Lacuna satellite system, and we've been mapping connections here from our static place in Copenhagen. All the colored dots on the European map here are places where we could contact the satellite, like the ground points over which the satellite is at that moment. And we then analyze the connections, we measure the RSSI. The connections went up to about 1,500 kilometers from a little box on my private home balcony. And we've done the same in deployments in East Africa. This is what this looks like. I'm not sure if you can see my pointer. If you can, I'm moving it around the satellite node at the moment. If you can't see it, it's the little white box tied to a stick in the middle of the picture. And in the picture on the left-hand side, a chicken is actually standing on that satellite box. So that's the actual device that communicates to the satellite network. Here's another one by a colleague and friend Fabien from Vietnam, where satellite terminals have been deployed in an agriculture field and are talking to the satellite from there. We've also started building our own satellites. We have a Danish CubeSat program, DiscoSat, and DiscoSat 1, which is being launched in a couple of weeks now. It will deploy some machine learning devices, Coral TPUs to space. DiscoSat 2, which we're currently designing, will have multiple LoRa boards, LoRa radios on board, and we'll be testing LoRa connectivity to our own satellite too. With that, so why should NRENS and why should APAN support this in any way? My best answer is actually grabbing some pictures of talks that we've heard in the last few days. One is from the introduction to APAN, APAN supporting agriculture, disaster management, Internet of Things. Then from the keynote, the problem of floods, of climate change. In all these fields, satellite IoT can play a valuable part. And that would be my reason for saying NRENS and APAN should be supporting this. In order to make progress happen here, what is needed? For one, of course, skills and capacity. And NRENS, I would say, are in the best position to help building this capacity. Then some terrestrial infrastructure is always needed, because when the data comes down, you will need all the conventional IoT data backends and so forth. Also for configuring devices, you actually need terrestrial LoRaWAN. Somebody needs to provide this, and again, NRENS would be in a good position to do this. Lastly, and very important, a clear regulations framework is needed. And NRENS could play a role in talking to regulators and trying to work towards an inclusive and open regulations environment. A quick word around about this. So around the globe, we're seeing a global harmonization around 3 or 4 frequency bands. They're not absolutely harmonized. You can see there's one dominating frequency regime in Europe, most of Africa too. The US has another one with 915 rather than 868 as the main ISM frequency. Then Latin America, Australia have another one. However, there's progress. Europe actually opens up for 915 now, so it's getting better and better, and that's of course very important for satellite networks. Looking at the Asia-Pacific region, and in particular at Nepal, unfortunately, we're currently in a situation where there is no clear regulations in place, which puts a stopper at all business opportunities and research and education activities in this field. So progress in this direction would be very, very important. I should also, at the very end, be honest enough to name certain risks with satellite networking. We're seeing an explosion in the number of constellations and launches, but we're seeing a lack of global policies. This is going very uncoordinated, and the chance of a so-called Kessler syndrome event, that means the collision of satellites with satellite debris, which might lead to a chain reaction of more debris spreading out and literally bringing down and destroying satellites, unfortunately, is a realistic scenario. You know the numbers of Starlink satellites. Collisions are getting more and more frequent. Just the other week, the ISS had to do a maneuver again to avoid a collision. We had a very, very close encounter of 2 big rocket parts. They missed each other by 7 meters estimated just a couple of weeks ago. There is risks in this uncontrolled growth of the satellite activities. However, exactly because of these risks, it's important that we help working towards responsible use of satellite technology in the interest of research and education and human interests at large. We can do so by engaging in dialogue with regulators, building capacity, and working on pilot projects together. That would be all from me. Thank you very much. And if there's time for questions, I'm happy to take these.
Thank you very much for your presentation. And do you have any comments and questions about the Sebastians? Kafres-san, do you have a comment?
Yeah, thank you very much. I am also participating from remote. It's a very useful and very informative presentation, especially related with the satellite. As you mentioned, Nepal may need such connectivity. One point I want to know is that you mentioned about DiscoSat and other CubeSats. So those are like the small scale, short life satellites, or you are mentioning about the commercial LEO type of constellation satellites?
Yes, so CubeSats are, it's a specification of a 10 by 10 by 10 centimeter satellite. So it's literally a box this size. It has a weight limit of 1.3 kilogram. And as you say, it has a limited lifetime. CubeSats typically live a few years at best, maximum maybe 5 years. And then they typically go into deorbiting and burning up in the atmosphere. Starlink satellites, although they're much, much bigger, they do the same. I mean, they have a lifetime of just a few years, and then they're being disposed of, basically burned up in the atmosphere. So yes, when you launch a CubeSat, you have to be aware that it will not be there forever. And the companies offering commercial IoT services are planning for this much the same. They constantly have to replace satellites. As a bit of a side comment from an environmental point of view, this is not without problems. We're burning a lot of metal in the atmosphere, and just Starlink activities will introduce tons of metal to the atmosphere every year. This is not without problems.
So may
But yes,
I
to
add,
answer your, they
Yeah.
are short-lived, relatively short-lived, and you have to plan for this when you're planning to deploy.
So may I
satellite
ask you additional question, follow-up question, one question. So when we have these short-lived small satellites, and for realizing some sort of real application, let's say tracking of tourists in the mountain. So how many satellites we need in a constellation, and how much would cost per satellite? So that may be the point many audience would like to know. Thank you.
Right. So I don't think it is realistic that we each launch our own satellite network. We do, from our university, have our little research project of building satellites and letting students learn how to construct satellites. But the idea cannot be that each country sort of launches their own satellite network. If, for example, Nepal wanted to explore satellite services, I would suggest that you talk to existing providers of satellite connectivity. And you asked about the price of that. Currently, it looks like all the companies offering this, they are in the range of $2 per device per month, $3 per device per month, in that range. It still changes very quickly because this market is still developing and it's only just starting now. But some few dollars per month per device. I currently have a student who actually works on a GPS tracker device with satellite connectivity. Now, this is the reason I wanted to be in the same room with you, so I could have shown you these in person. This is one of the Lacuna terminals. And you could imagine if this was strapped onto a backpack, for example, and it's battery driven and it lives for many, many months on one set of batteries, then this could be the kind of device that helps us track tourists, trackers, whoever it might be in remote mountains.
Thank you. Thank you so much.
Okay, thank you very much. But the time is a little pushing, so we need to move to the next speakers. So thank you very much, Sebastian.
Thank you.
And the next speaker is Naveed Arshad.
Thank you very much.
So if you're ready, please start your presentations.
Sure. So let me know when you can see my screen.
Yes, we can see.
All right. Thank you very much to organizers and dear fellow colleagues from APAN. So I'm sorry I'm not there in person. I wanted to be, but I have some other back-to-back travels which prohibited my traveling to Nepal. But hopefully through technology, I'll be able to deliver some of the work that we have been doing for the past couple of years. And now that work is taking shape and like to share some of that knowledge with you. So this work that we did is in partnership with, of course, with the funding from Asia Connect, with the Teen Corporation Center. Our partners here are the Ministry of Malaya and the PER Network from Pakistan, as well as the Ministry of Climate Change of Pakistan that has been part of this work. So the goal for us is to develop sustainable air quality monitoring with low-cost mobile sensors. Now, air quality monitoring is not something new. I mean, there is a lot of research that has been going on, but we wanted to use air quality monitoring through sensors that we can move around rather than at a fixed location. So unfortunately, the area of the world that we are living, I mean, in Pakistan, India, Bangladesh, Nepal, I mean, there's not one of the best air quality that we face here. It's can say one of the worst air qualities that we have in this region. And the city where I am currently, Lahore, is unfortunately the most polluted city. It was second or third, but now it is unfortunately at number one, just reported 2 days ago. And in November or December, when the temperature cools down, we have this season. It's a fifth season, fortunately, that we call the smog season, when this fog-like thing just, I mean, is in our air, and that blocks a lot of delayed flights and lots of challenges that we face in that region. But although this is visible to plain eye at that time, the air quality is a challenge throughout the year. In the summer season, because of the warmer air, it just because through the current it just moves away. But the sources of pollution, the sources of air quality challenges are still there. So Pakistan, of course, is the fourth out of the 243 country in terms of pollution ranking, and this is not something rosy scenario, and not just Pakistan, but the whole area of this plain is actually susceptible to this. As I said 2 days ago, I mean, it is now declared the officially most polluted city, and in terms of air quality. Now, there are significant health challenges that come with it. One obvious one, of course, is premature death because of the outdoor and indoor air pollution, but there are many other challenges in terms of health. So one that has been found out recently is a relationship between Alzheimer's and Parkinson's with the air quality. And other than pulmonary diseases and others are quite common, especially in those seasons when the concentration of pollutants is pretty high. But the question is, what can we do? The first thing, in order to improve air quality at any location, it's to, of course, measure it, that what kind of sources are there, what is the air quality through different times, through different seasons. Unfortunately, we do not have those kind of, or a network of those sensors that is available. And I'm talking about really high cost, you can say calibration level networks or air quality sensor that are available. There are a bunch of privately based air quality sensors that are deployed by, you can say, the general public, and those that is available, but without any kind of reliable air quality and sufficient air quality monitoring, it's kind of a blind surgeon operating on a patient. So that's, of course, is not a sustainable situation. So in our earlier project, which is real-time spatiotemporal monitoring, we ventured on to develop a real-time air quality monitoring system through a spatiotemporal technique, which means that we'll have the sensors deployed on vehicles, and those vehicles, when they move around in the city, they will send us readings about their quality. And rather than having a sensor network that is spread around the city with fixed sensor, we have these mobile sensors that can go around. And of course, we would like to develop a blueprint of developing this system that can help us in not only replicating this system in other countries, but also in mitigating and adapting not just challenge of air quality, but on a wider scale, challenges of climate change. So the initial idea, which was a strawman idea, was to divide the city maybe in a grid-like structure and have whenever the vehicle passed through a particular space in the grid, that region air quality is measured through the vehicle, and then it's reported. And as multiple vehicles pass through it, we can just average out those numbers, and then we can develop over time a spatiotemporal quality map of the air quality in the city. Of course, that was the initial idea, but later we realized that that's not something that's not as straightforward as it can be. And I'll talk about it in later part of my slide. About the architecture of the system, so we have these dual network, which is of stationary network, and that's also the mobile sensor network. Both of them currently connected through a 4G network to provide information to our PERN network at the Higher Education Commission. And then it is then reported to the public through different channels like Portal and others. And also it's reported and stored the data at an open data portal that we have, and also reported to the Ministry of Climate Change as well as Environment Protection Department. So in order to develop those low quality sensors, we also realized that in our previous projects, if we just buy a low cost sensors, I'm not saying low quality, but it's low cost sensor from abroad, first of all, the procurement is a challenge, the after sales service is a challenge. And then of course, those sensors were only reporting one type of input, and that's only the particulate matter. So what we wanted to do is to develop a sensor that can actually measure multiple types of pollutants. And for that, we then asked a local vendor, a local company to develop a co-design a system with us. So the picture that you see in front of you is a system that we developed. This is a sensor that is measuring 5 different pollutants, which including both PM2.5 and PM10, ozone, NOx, SOx, and carbon monoxide. On top of that, it also measures temperature, humidity, and also provides the GPS coordinates of where it is. To power it up, we wanted to have a self-contained system, which consists of a battery as well as a solar panel, so that whenever the sensor is out in the field, it can generate its own power. It's not dependent on any external sources of power like something coming from the vehicle. So this sensor, depending on what source is available, it can charge from a solar panel, it can charge from a battery, it can even charge from the grid if for a stationary sensor that is available. And then there is, of course, a structure that I'll show a little later in the presentation. Along with that, we also developed a platform, airlens.com. This is platform. If you go to this website, you can see a few things, although this is that is a work in progress at this time. And then we using these numbers that are coming from these different values of different pollutants, then we use the US EPA method to create an air quality index that then is reporting it in terms of hourly or daily values. And our hope is that this AirLens platform provides a spatio-temporal measurements of air quality in the city, so that the public can be aware and the government can take interventions as they feel like. Then, I mean, going back to my earlier point, dividing a city into grid, which is just a normal grid, is not really that accurate. And the reason is that there is an administrative structure of the city itself, right? And that administration in our city, there is 9 zones, and then there are sub-zones that we call union councils, and there are 274 of them. But then there are some regions of interest there, which is where the residential density is there, some areas where the traffic density is there, some areas where public buildings are there, because you cannot just install your stationary sensor at any location, and then the security of the sensor, and then the people who can volunteer to install those sensors. So all those actually were the challenges that we faced. So using some information or these, you can say, challenges, we developed our own algorithm of dividing the city into different spatiotemporal zones. And in our first exercise, what we did was that we developed 40 sub-regions of the city, which then can be monitored for spatiotemporal air quality monitoring. And we made a video, I'll send out this link, where you can see that what kind of algorithm we followed in order to develop the whole city into these regions, which takes care of high density and air traffic, the road traffic and others. However, we face numerous challenges when we were doing it. I mean, as naive as we were at that time, that there are 2 kinds of emissions. One is an ambient air quality, and then there is an on-road emissions. So on-road emissions is always in the between 0 to 30% more than the ambient air quality, because the pollution sources are right there. So if you are measuring, let's say, a sensor that we install on a vehicle, we are not actually measuring the ambient air quality, but we are measuring an on-road emission, and that on-road emission also, we cannot just reduce the 30% value from it and get the ambient air quality, because it has a different spectrum of percentages, which is depending on how much pollution sources are around. So that was number one challenge that we faced. Number two challenge that we faced was that all the public transport, at least right now, is based on fossil fuel vehicles. So we wanted to install them on top of buses, which are all diesel operated. So their self-emissions can obstruct the reading, they can exaggerate the readings. And then public transport is not running all the time. It is depending on how many passengers are around. So in daytime, yes, they have enough operation, but at nighttime, they do not operate. And holidays, they operate with a less schedule. And the most important thing that when you are doing this kind of a citizen kind of involvement of in kind of air quality monitoring, the sustainability of the sensors is always a problem, because this is not a for-profit activity. So how do you sustain it other than getting funds that you will need all the time? And then finally, we actually ran into another problem, that while our system was ready and we were ready to deploy, because many people were doing these private readings, so the government said, and of course, for the government, it is kind of embarrassing that the people are telling them that we are living in the most unhealthy city in the world. So they, of course, then developed some cyber law to prevent people from reporting these. So we got this letter from, a year ago or so, that you cannot, whatever you measure, you cannot publicize your data of air quality measurement because this is not government approved sensors. And that actually, kind of just jeopardized the whole project. But of course, we tried to find ways to go around it. And we said that, okay, this is an umbrella of R&D. We are not going to be reporting it for any kind of government intervention or what any kind of law development, but it is at least information that that we want to do. So then we, of course, work with the regulator and try to find out way in which we can report these sensors and take it to the public and also be a useful source of information. So this is, so we then developed the stationary sensor. So we find out 8 different areas in the city where we can install the stationary sensor. So these are the 8 areas. On the left side, you see the different map of the spatiotemporal region, depending on the other earlier parameters that we developed. Then these are some of the pictures from the sensors that we installed at different locations. These are actual sensors that are providing us values, but again, on a stationary basis. Another critique that low-cost sensors always face is that whether these are reliable sensors or not, right? So in order to make sure that we get to the reliability or adequate reliability of these sensors, we did another exercise, and that was with the regulator, that we had a co-location activity. So co-location activity actually works in the following way, that you have these industrial strength calibrated sensors, and you put your sensors with them for a certain period of time. And you check that whether the readings that are coming from the calibrated or high grade sensor is in what range different from the low cost sensors. And if the range is not maybe 1%, 2% difference, then you said that, okay, there's good enough reading that you're getting from these low cost sensors, which will help you to record data. So we developed these co-location activity. They were kind enough to give us their van, which is actually a mobile van for air quality sensors. And we placed all our sensors with that van, and then we performed the co-location activity. And in the meantime, we also won the project in the second phase of the project, where we said that, okay, we're rather than using the vehicles that are based on fossil fuel, we'll use electric vehicles to monitor these air quality. And then we will we'll kind of develop a system where we will be using these mobile sensors on top of vehicles as a stationary sensor as well as a mobile sensor. So we'll get best of both worlds. And let me tell you how do we do this. And also to develop a business model which can sustain the whole platform beyond the funding that we have at this time. So we found the best and the cheapest way to install a sensor is a three-wheeler, which is a common mode of transport in almost all cities of Pakistan, and it's you can say that's very common, and they go to areas where other vehicles cannot go. And then will extend the platform so that we can get information from other sources about their quality as well, rather than relying on just our own sensors. So this is an interesting, you can say, map that will tell you that how we transformed our mobile sensors to mobile plus stationary world. So on the left-hand side, if you see that we have this, this is our original plan is to install the sensors on buses. And if I can have a pointer, yes. So if a bus goes along, so this will just read all the values on the road emission, and this is you can say a densely you can say traveled road. And the bus should have been reading all it. So the challenge here is that the bus is only reporting the data from one particular road only. And then there is one route, but there's another route. And all this area, which is maybe in the neighborhoods, is all actually we do not have getting any reading from there. Using the three-wheelers, we switched the project a bit, and we said that, okay, we'll start our journey from, let's say, a normal bus stop, and then it will traverse. And by the way, this route and this route is the same. So we travel from this area, but this is the last mile connectivity, you can say, vehicle. So it will go inside the neighborhood, areas which is the less, you can say, which has less traffic density. In fact, in some areas, there's almost none traffic, especially in front of parks or others. And it will stop at different points, not only to just take passengers, but also to record a stationary reading there. So while the vehicle is moving, it is sending us the data as a mobile sensor. And when it stops there for a few seconds. And the reading at that time will give us a ambient air quality at that region. So we are getting both the stationary reading as well as reading from the mobile world. And then we developed these routes, different routes along the major highways. So it almost got us rid from the you can say the on-road emission problem. So yes, we are recording some on-road emission, but when we go inside the neighborhoods, we are getting a better ambient air quality. And then we have a separate network of stationary sensors. So all these mobile sensors, mobile plus stationary sensor, and fixed sensors are all providing data of different kind. And then we extended this platform to develop APIs so that we can get data from other platforms which are available, for example, IQ Air and Purple Air and others. And then all those numbers and all those data can be displayed on the AirLens platform. The project was supposed to start last year, but due to some procurement issues, it got delayed. These are the very first vehicles that we have now. And if you see that we have, so the problem is that we cannot install the sensor anywhere on the vehicle. It has to be up in the air so that there is an unhindered airflow through these sensors. And they have to be about a human height. So this is about 6 feet tall, these vehicles. And just on top of it, we have put these sensors, and then there is the solar panel on top that is powering them up. And now we have these vehicles on our disposal, and then we are running these vehicles all around in the city, not in the city, but in a small neighborhood, to check that whether the readings are up to our expected standard or not. And again, we'll run this pilot project for about 6 months. There was a talk about in the earlier presentation that the difference between using 4G as well as the LoRaWAN kind of network. So in Pakistan, we have this challenge that 4G is easily available, although it's expensive. Coverage is good in cities, but if you go outside the city, it's a bit patchy. And then you're dependent on a network provider. But there are a couple of problems here. One is that whenever we have a VIP movement, typically there are jammers that just jam any kind of communication, so we don't get communication at that time. And then there are certain network blackouts. These network blackouts are not because the electricity is not available, but because of maybe some political activity or something. The government just blacks out the whole network. So you're not getting anything or any signal, and you just lose all these values. Not lose all these values, but at least you not receive all these values for that duration of time. Just last year, the government has decided to provide IoT licenses. So these are cost effective. But of course, we'll need coverage because the vehicles are going around, and we'll have to have some stationary, you can say, places where we can actually send the signal, and then through a gateway we can upload it. But there are licensing issues with it. So open band, the only open band that we have available is 433 megahertz, and that's that range is not enough for us to install. We have to install many of them in order to use this range. But then, because now we have IoT license, we can apply between 220 megahertz to 915 megahertz, and we are in the process of getting the license and shifting our network from 4G to LoRaWAN. Now, finally, the sustainability of the project. And this is something that's very close to my heart, that whenever these initiatives start, they actually just stalls when the funding ends. So what we are using now, we are piloting on that, is that a three-wheeler is a commercial activity. And we are providing this activity and in kind of gaining some kind of revenue. And that revenue, 25% of it, we are setting aside for the maintenance and the upkeeping of the sensing platform. Because every sensor that we have requires a calibration after every 1 year or 2 years, depending on the quality of the sensor. And after some time, we just need to replace the sensor. Although the device is there, but sensors that are monitoring the air needs to be replaced. So this 25% of the vehicle revenue, we are setting aside so that this can stand on its own feet. So while the sensors are provided, the project and the vehicles and the air quality sensing can go a long way in getting the revenue through which we can actually generate, you can say, a longevity of this platform. So this is it from my side. Thank you very much. And I'll be happy to discuss further, either now or later. Is my email address and my phone number. I mean, this phone works on WhatsApp. So if you like, we can also communicate on collaborating collaboration opportunities. Thank you very much.
Thank you, Navid. And do you have any questions and comments for his presentations? How about the virtual participants? Okay.
I have a question about your business model. So what could be the benefit from a three cycles driver services that can get from the air monitoring your system?
So if I understand you correctly, you're talking about how the business model works? And
yes, because this is kind of you are providing the sensor equipment, right? To a company like a riders with the three cycle wheel.
Right. So
and then you're gonna get a 25% share revenue from their companies.
So so the silver lining that we have over here is that in a fossil fuel world, the three-wheeler that runs on fossil fuel, so if I give you the actual number, in Pakistan with the current fuel rate, the fossil fuel drivers can have to spend about 18 rupees per kilometer on fuel and maintenance. 18 rupees per kilometer. If we convert it to EVs, they have to pay 4 rupees a kilometer, almost 1/4, even less than that, almost 1/4 of the operation maintenance cost. So there's a large differential there. Of course, the drivers who are getting these EVs through government incentives or through another initiative that I'm working with, they're getting these EVs through some mechanism and they are getting the benefit. But part of the benefit we are trying to park for this kind of activity. So the drivers are getting much benefit, and we are just taking part of the benefit so that we can use it to make this platform more sustainable. So essentially what we're doing is the efficiency of the electric vehicles is helping us.
Okay, any other questions? Okay, thank you very much for your presentation. And this is the final presenters, and the time 15 minutes already passed of these sessions. And thank you very much for your all attendees, participants. And thank you very much also the presenters. And I will close this IOT working group sessions.